Example 4.2.2a. For the transformer connection shown, determine the three-phase configuration and draw the associated phasor diagram. Assume that the transformer has a primary reference voltage of 1 angle 0 degrees volts and that the turns ratio is 1.1. So the purpose of this example is that we're really trying to show that three-phase transformers can be thought of as three individual transformers wired together either in a delta and a Y, and there should also be some recognition that the way that they are wired together in either in a delta Y will influence the output voltage of the system. And we want to be able to understand and calculate what that relationship is going to be. Are the output voltages directly related to one another via the turns ratio, or are there other intermediary calculations that need to be done, such as converting between line to line and line to neutral, and then is there any lag or lead in the system? So let's go ahead and dig into it then to solve this one. So here we've got the transformer here, and you can see that it's a three-phase transformer. We can tell that it consists of three individual transformers here, one on the top, one in the middle, and then one on the bottom. And each of the individual transformers is, of course, labeled according to the American Standard Transformer Notation, where we've got two terminals labeled H1 and H2 on the primary, and two terminals on the secondary labeled X1 and X2. And on all of them, they're labeled with the dot convention. Just remember that if current flows into the dot, it will induce a voltage that is positive at the corresponding dot on the secondary side. So that's what that means. And that will be important for this. So what we're trying to do is we're trying to figure out by this diagram whether or not, or what sort of transformer configuration this is. So how I like to start about that is I like to label the connections, and what I'll do is remember on the generator side we typically labeled things with lowercase, so I'm going to continue that on the primary side, and I'm going to label the three nodes there A, B, and C. And then also from our three-phase analysis that we did in the last chapter, we tended to label the load side with capital letters, and so I'm going to use that same style over here and label that A, B, and C, and then we can see that this X0 node is labeled with a ground symbol right there, so we'll just call that N. So that's going to be helpful in determining the transformer configuration. So what I want to do next is just identify each of the individual transformer nodal calculations, and I'm going to assign each terminal a 1 or a 2. For example, A1 or A2 or B1 or B2, etc. Ones are going to be assigned to the terminals connected directly to the letter, and twos are assigned to the opposite terminal of the same coil winding. So I am going to come here and I am going to see, for example, this is A right here, and I am going to say, okay, that is A1. It's connected directly to A, and I'm going to call that A2 right there. Actually, you know what? I'm going to move it. I'm going to put it right up there. That's A2. And then this is A1 here, and since this terminal is directly across from A, I'm going to call that A2. And then this one here is connected to B, so that's B1 and B2. Here that's B1 and B2, and then that's connected directly right there, so that's C1 and C2, and then that's C1 and C2 down that terminal right there. So now I'm going to use those A1 and A2, B1, B2 connection labels to draw three single-phase connections for each side of the transformer. So I am going to draw that, basically the left-hand side of each of those. I'm going to represent it like that. All right, so I'm representing just one side of the transformer there, and then over here I've got the secondary side of the transformer represented there. And I am just going to label the different connections. So for this top transformer, I can see that it's connected to A1 and B2, right? That node right there is labeled both A1 and B2. This one is labeled A2 and C1. So again, I just look right here. Definitely A2. I follow that line right there. It's also C1. So that's this top transformer. I come down here and I see that this is B1, C2. I come down here. This is B2, A1. So that's that node. Then this transformer right here I see is C1, A2. And then the bottom one is C2, B1. Okay. Got a little tight right here, so I'm just going to move that over a little bit, give myself some room. I'm just going to repeat that on the secondary side. I see this top node is just connected to A here, and then that one goes to N. Here it's just connected to B. Sorry, there's ones there. And just connected to N on the other side. Here it's C, and that side's connected to N. So C1, N. So now what you need to do is just connect the nodes with the same labeling to form your three-phase diagram. So I've got an A1, B2. So this node here and this node here are the same. So I can draw that node, and I've got A1, B2. And then there's another node coming off that. This coil here is this here, so that means this node here is C1, A2. And this coil here is this coil here, so that means this node here is B1, C2. And that leaves the coil that connects from B1, C2 to C1, A2. That goes right there. So I can see that the primary side is a delta configuration. And then if I look at this, I can see that the only shared node over here is a neutral. So that obviously has to be a Y connection. So we've got the mechanism or the method by which we label each node of each side of the transformer with a unique identifier, and then we see how those unique identifiers connect. So that tells us that this is a delta/Y transformer. Delta on the primary, Y on the secondary. Okay, so now what we want to do, now that we know it's a delta Y, we want to determine what the phase relationship is, and normally we represent that with a phasor diagram. So I'm going to scroll back to the top here, and I've got my transformer diagram here that we've been analyzing. So the question is what's the phasor diagram look like for this? So the technique we want to use here is that we want to start by just picking a reference voltage on the primary side, and it's pretty much we'll choose the A phase on the primary side. So if it's a Y connected generator, transformer on the primary, we'd use VAN as our primary. If it's a delta connected, we're going to use VAB as our reference voltage. And so we have already determined this is a delta connector, so we're going to use VAB. So our task is to find out which one of these coils is the VAB coil in the delta, right? And so we know that this is A node here, and this is B. So this coil here, I see one side of it's A, the other side of it's C. So if I measure from here to here, I actually will get VCA, so that's not it. If I come down here, I see that this node here is B, and this node here is A. So if I measure from here to here, or that's actually from here to here, that's VAB. So that's it right there. This is our reference coil right here. In fact, I'll clear this up a little bit by erasing those. So this node here is node A, and this node here is node B. And just so we are thorough, we come down to this one. Well, what voltage appears across this transformer? This is V, we can see B to C right here. So this is going to be our reference transformer. So in an ideal transformer, the output voltage is in phase with the input voltage. So VAB is our input voltage here. It goes from this node to here, and it induces a voltage that is positive from here to here. Well, that's NB. So VAB is going to be equal to VNB in this transformer. Right. Well, it'll actually be equal to the turns ratio times VNB. But to develop a phasor diagram where we're just trying to determine if something's lagging or leading, we're just going to assume that turns ratio is 1:1. So those are equal because this is a 1:1 transformer. So VAB equals VNB. Well, what we're trying to do is figure out what is the relationship between VAB and the phase A voltage on the secondary. And we don't have that. We have VNB, so we need to do a little bit of math there. So just remember that. I'm going to scroll down and we're going to start doing some math. So we've got VAB on the primary side is equal to VNB on the secondary side. And we need to somehow convert that to something that is on the A phase. So we want to know probably what V capital AB is, right? That would be make the most sense. So let's go through that math. So the first step is, well, VNB is backwards. We would normally measure the voltage from node B to N, not from node N to B. So I can just write that as equal to negative VBN, which is equal to VBN times 1 at angle 180 degrees. So those are just simple mathematical substitutions for the negative sign so that we can use BN instead of NB. All right. So we know that in a three-phase system, we can get VBN if we knew VAN. Three-phase systems are always 120 degrees out of phase. And the relationship is that in the three-phase system, the B phase to neutral value, or the phase quantity, is equal to VAN, and we're using a ABC phase sequence, so that's VAN times 1 angle negative 120. So what I can do is I can just plug this value in for VBN. So I get VAB is equal to VAN at 1 angle negative 120 degrees times 1 at angle 180 degrees. And so if I multiply those two together, I just get VAN times 1 at angle 60 degrees. So I put an input voltage on VAB, and my output voltage is going to be, if I measure from VAN, is going to be 1 at angle 60 larger. So it's going to lead by 60 degrees right there. So remember, transformers aren't typically rated on a line to neutral quantity, no matter whether it's delta or Y. We typically do that on a line to line quantity. So the next step we want to do is we want to convert this VAN over to its associated line to line quantity. And so what we know is that VAB, since this is a Y secondary, is going to be equal to √3 at angle 30 degrees times VAN. That's just my standard line to line conversion for a three-phase Y system. So obviously I want to solve for VAN, so I can substitute up here, and I get VAN is equal to VAB over √3 angle 30 degrees. So then I can just plug this value for VAN up here, and I get VAB is equal to VAB on the primary over root 3 angle 30 degrees times 1 angle 60 degrees. And I multiply those together and I get VAB is equal to 1 over root 3 times VAB at 1 angle 30 degrees. Now, usually I want the output in terms of the input, so I'm going to solve for VAB on the secondary side, and that is going to be equal to VAB on the primary side times root 3 at an angle of negative 30 degrees. So what that tells me is that the output voltage on a line-to-line quantity for the transformer that we showed above is equal to the input voltage on a line-to-line quantity times the turns ratio, which in this case was 1:1, times root 3, and it lags by 30 degrees. So not only is there a root 3 change here, but there's also the output voltage is going to lag the input voltage by 30 degrees. So the analysis shows that the secondary line voltages are lagging the primary line voltages by 30 degrees. So I can use that information now to go ahead and draw basically the entire phasor diagram. What I would do is start with the reference VAB on the primary, and we know that VBC and VCA are all going to be 120 degrees out of phase with one another. I just determined that VAB lags by 30 degrees, so this is going to be a 30 degree phase shift right there, and that's VAB. And 30 degrees from here is VBC, and then 30 degrees from negative 120 is plus 90, so we get VCA right there. So that is our phasor diagram for the transformer that we have. So we've got the primary side voltages, VAB, VBC, and VCA, and then we've shown that the secondary voltages all lag the primary voltages by 30 degrees. So we've got our phasor diagram for our transformer.